We've invented a flow integral, so now let's see if we can invent an integral that will measure how much a vector field flows across a curve. The name for this is flux. Right? Flux is how much something flows through something else, and so we will call this a flux integral. To give us something concrete to think about, let's take this vector field and let's traverse a curve that starts here and goes to the upper right. Okay, you can see that that this vector field is flowing across this line segment. We have to decide arbitrarily which direction we count as positive flow, and we will choose positive flow to be to the right as we face the direction of the curve. So all of these, the vector field in this diagram here, the vector field is always pointing to the left as we face up and to the right. Right? We are traversing the curve, moving upwards and to the right. So as we face up and to the right, the vector field is pointing to our left, and so this flux will actually count as negative, not positive. Okay, so positive flux will be to the right. And then also faster flow should count for more. So out here, further away from the origin, this should have a larger flux, and the portion of the curve closer to the origin, this should have a smaller flux. Okay. There actually is a good reason why flow to the right should count as positive, and it's because in many applications, the curves that you want to, and we'll get back to this later in the quarter, but in many situations, the curve that you want to measure the flux across actually is a closed curve that forms a closed loop. And in this situation, we will want to measure the flux of the vector field flowing out of the region and not into, right? At least that's the choice that we made when we measured divergence, right? Positive divergence is flow out, so we ought to stick to that when we talk about flux. So it should be flow outwards that counts as positive, but which way is outwards, to the right or to the left, depends on which way you go around this loop. But when we go around a loop, we typically count counterclockwise as the positive direction around the loop. So if we want the positive direction if we want positive flux to result from outward flow when we go around this loop counterclockwise, positive flux has to be rightwards and not leftwards. So that's why we're choosing rightwards flow to count as positive. Or sorry, rightwards flux to count as positive. Okay. So just like when we invented a flow integral, all we need to do is measure at a single point. If we can measure these things at a single point, then we can just do a line integral, a scalar line integral, to get the total flux. Okay, so let's see if we can measure the flux at one point, so at a single point along the curve. Okay, well, right, flow to the right, we could detect flow to the right if we had some vector pointing to the right, some unit vector pointing to the right that we could take the dot product with, right? Much like we measured flow along a curve by dotting with the unit tangent. We could measure flow to the right if we had a rightward pointing unit vector, and that would also, and since it's a dot product, that would also get bigger when the vector field gets longer. So what we need to do is take our vector field dotted with some unit right vector, right? Some unit vector that points to the right. And it's a little tricky to know how to come up with such a vector, right? We have this unit tangent vector, which is capital T, and that was r prime over the length of r prime, right? But and that points along the curve, but how do we get a vector that points to the right? Well, in the plane, there's kind of a nice trick. So r prime is x prime comma y prime, so that over magnitude of r prime. All we need to do is give this unit tangent vector a quarter turn to the right. And there's a nice trick for doing that. It turns out all you need to do is, so this is going to be our new vector that points rightwards. So a rightward pointing unit vector, unit. Okay, and we're going to call this the normal vector. Okay, and the trick for coming up with it, we'll actually use the length of r prime, but what we will do with the components of t is we'll just switch them and make one of them negative. So we'll put y prime over here, x prime over there, and then we also need to stick a minus sign on one of these. Which one we put the minus sign on will determine whether we get a vector pointing to the left or pointing to the right. And to get our vector pointing to the right, it turns out we need a minus sign right there. So that will be our unit normal. You can tell that it is perpendicular to the curve because if we take the dot product of n and t, we do indeed get 0, right? Because you get x prime times y prime minus x prime times y prime. That's 0. So these two vectors are perpendicular. To convince yourself that n points to the right and not to the left, one way to do that is just use an example. Take this vector, 1, 0, and then switch its coordinates and stick a minus sign on the second coordinate. You get a vector that is perpendicular to the one we started with, and it's been rotated to the right 90 degrees. So by sticking the minus sign on the second term here, we are getting a unit vector that is pointing to the right and not to the left. Okay, so remember we invented this unit normal vector so that we could dot f with it. So to measure the flux at a single point, we just need to dot f with n. Okay, so that measures the flux at a single point, and then the total flux is of course just the integral of this. So the integral of f dot our unit normal ds, right? So f dot n, this is a scalar. So once we have a scalar, we can do our scalar line integral. Well, so this is fine for an idea for what we want to integrate, but to actually perform this, to actually calculate one of these integrals, as usual, we need to parameterize this integral. So, I need a little c here to say that we're integrating across some curve. So to parameterize this, we have to get a parameterization r of t, so a parameterization of c, of our curve. Right? That will come with some bounds that tell us what t values we need to trace out the curve. So our bounds will be a and b. So we're going to integrate f dot n. Remember, n is y prime comma minus x prime over the length of r prime. And then ds is the length of r prime dt. Well, just like when we invented the flow integral, this inconvenient magnitude of r prime now cancels, and we get the integral from a to b of f dot y prime comma minus x prime dt. So this is when we actually calculate one of these things, and when we actually calculate a flux, we will use this parametric form of the integral. Of course, I'm using a little shorthand here because really everything is a function of, well, f is a function of position, and we need to use our parameterization to tell f where we are located at any particular time. And y prime and x prime, these are really functions of t. Right? So to write everything out in explicit detail, it would look like this. Okay. This happens in vector calculus a lot, where things can be functions of time and position and other things later in the quarter, and so often we will suppress all of our sort of function notation, and we will write things just to make things shorter so that it isn't such a mess. But the cost for doing that is that we have to keep track of what everything in this expression is and what it is a function of. So it takes a little getting used to, but it's worth it, because writing everything out in gory detail like this every time gets to be very annoying.